For waiting and sorry for the delay. Let's get started right away. So, new topic, derivatives. Before we start, are there any questions? Yeah, so we have only about 40 or so people turning up. I just hope that the rest of the people are having an easy time, or maybe or looking at the lectures independently afterwards, or self-studying. I'm not quite sure what's going on. The first homework is anyway around the corner, and which will be longish because we went for a little while without a homework. And maybe I will require every one of you to meet me during office hours, even if it is just for 2 minutes. You can just tell me everything is going okay. And anyway, so let's get started. And so let's write down the definition of the derivative. So here, so we should start recording.
Recording in progress.
Okay, so we all know what a derivative of a function from real numbers to real numbers is. Let's write this down. F prime of A is limit as h approaches 0 of f of A plus h minus f of A divided by h. Okay, so this is all fine. But for this to make sense, what does f need to be? So f is a function, real valued function. For this to make sense, so this is the derivative of f at A in R. So for this to make sense, does f have to be defined on all of the real line?
No.
No. But it cannot be defined only at A, right? So what does it have to be defined on in order for us to be able to calculate this limit? Assuming it exists, but
A ball
in an
around
open
it.
ball around A.
right? So you see, you want to be able to take the limit as h approaches 0. So, so let's just write this down. F should be defined in some neighborhood, right? In some A minus something to A plus something. So A minus, okay, let's call it epsilon. Okay, so the thing is, and here's the problem. I want to have this same definition make sense. If f is now a function not from just real numbers to real numbers or some subset of real numbers, but really a could be a point in some m-dimensional space, and the function could take values in some n-dimensional space. So it could be a function of many variables whose value is also a tuple, right? So so can we make sense of this? So how to so let me first just write this down, i.e. f is a function from some neighborhood of A to R. So you see, this definition of neighborhood is useful. The domain of f does not need to be open in order for me to define f prime of, in order for me to even conceive of defining of f prime of A, but it needs to have an open set around A. contained in the neighborhood. Okay, so the thing is, how do I generalize this, where the left hand side is also not part of R, but some high dimensional space. And the function also takes values in some high dimensional space. So what we want to do is the following. So definition of for in R, in some RM, let's say, to Rn. And the reason why I took the domain to be open is because then I can wonder about the derivative at every point in the domain. Okay, so just look at the definition up there and see if it makes sense. Does it make sense?
So the normal difference between them does not make sense.
Yeah, so there are various things, right? So f of a plus h minus f of a. Does that make sense? Okay, so let's go one by one.
H is not.
Yeah,
H is not a real.
Yeah, so h is not a real number. So in this case, so you see a. So there are some difficulties here. So let's consider. So here a is in Rm, but h is also in Rm, correct?
Sir, you are considering the function from Rm to Rn, right?
Well, so really speaking, so this some open set in Rm to Rn, right?
Okay.
Okay. So A and H both need to be in Rm. In fact, what needs to happen is that A needs to be in U and H needs to be something small, as small as necessary, so that A plus H is also in U, right? But that is okay because A is U is an open set. So there is wiggle room around that in all directions. Yeah, I can put a ball around that while staying in. Okay, so f of A plus H makes sense. It is an n tuple. How about subtracting f of A from that? Does that make sense?
No, sir, we need to have norm.
Why? So can I subtract? So f of something is something in Rn, right? So can I subtract two things in Rn, one from the other?
Sir, we need to define what we mean by subtraction.
Yeah. So can we subtract one point from in Rn from another?
Yes, sir.
Yeah, it's a vector space, no? So I can subtract. There is no issue with subtraction. But there is a bigger problem over there. So far, I'm good. So such that A.
But actually, we know that we can subtract and we will get another term in Rn itself. But
Yeah,
how we
okay.
subtract, that depends, right?
Well, no, Rn is a vector space. So really, I mean, you can define any operation you like, but really there is a natural operation here.
Oh, okay.
So f of A plus H minus f of A makes sense. And where is this? This is something in Rn, right? But what happens next? I want to divide this by H. Does that make sense?
F is in Rn, but H is in Rn.
Okay. So now this is even, so there are the various problems. They are of different kinds. The f of whatever you are taking is in the target. It is in Rn. whereas H is in Rm. But even before that, what does it mean to divide by a vector? So which is a vector in R. It's a pretty big problem, right? Okay, fine. All right. So let's leave that aside for now. How about taking the limit as H approaches 0 of whatever? Does that make sense?
So since you are considering neighborhoods, there are multiple ways of approaching.
Right. Right. So there are multiple directions. But really, so the way I can think of that is that from all directions, if I can approach something or the other should happen. Or to reduce to one variable situation, the limit as H approaches 0, maybe should, so is there a way to say what it means that H is close to 0?
The norm of H tends to be.
Yeah, right. So I can think in terms of norms, right? But this also maybe tells me something that when I divide by H, perhaps I can think of dividing by the norm of H. So you see, I'm just sort of throwing out various ideas, all right? But anyway, let's put that on the side. And let's look at, see, if you do not know how to do something in general, then maybe we'll look at a particular case. So, okay. So let's see if I can maybe we do this or not. Okay. So special case. So what if we have more specially? So case when, let us say that instead of going from Rm to Rn, suppose I let one of these numbers be just 1. Then which one is going to be easier, to take m equals 1 or to take n equals 1? Look at the definition up there and see for which case the problem kind of goes away.
For m equal to 1?
Right, because then you see H is now just a real number. And so I can, so let's say it this way. If m equal to 1, can adapt or use the same definition. So f is vector valued, but H is still a real number. So in this case, I have f, which is some open U in R. And I'm going from that to Rn. But you see, so this point A in here is going to go to a tuple, but really speaking, it is just n different functions, correct? And in this case, what turns out to be the case? So f prime of A will simply turn out to be, and we can say, and we get, which is using the same definition. What do we get? F prime of A is what kind of gadget here? Just look, f of A plus H is a vector with n slots, as is f of A. And I subtract, I scale it by the scalar 1 by H and take limit as H approaches 0. What kind of gadget do I get?
We get f1 prime A, f2 prime A.
Exactly. So f1 prime A But there is a little bit to say here, right? Which is that how do I calculate a limit in this target vector space Rn? So there are a few words over here to say, right? And so how do I calculate limit in this vector space Rn? What does it mean that a sequence of, what does it mean that a vector valued function, a vector valued function approaches a certain vector? How do I make sense of that?
So we see the slot-wise convergence after taking the difference.
Okay, so is that your definition? Or yeah, you can use that as a definition, but we actually have a better answer, which boils down to what you just said. So
Sir, the norm approach is 0.
yeah, so you see, I can very well calculate limits in a normed linear space, correct? Yeah. So if I have, remember that in fact, I have the notion of a limit of, if I have, in fact, even in metric spaces, I have the notion of a limit, right? So limit as, so let's write this down, recall. I have the definition of limit as whatever x approaches a of f of x equals some value, I don't know, b in y. Means, what does it mean? Come on, this should be,
For all epsilon greater than 0, there exists delta such that y d of yx is less than delta implies d of
so d of, yeah, so d of x, y. Let's not use, no. So sorry, that didn't come out right. So what should happen? D of,
X comma A.
D of x comma a less than
delta implies
d of,
f of x b less than epsilon.
so with this in mind, just look over here. Does the statement make sense? Because now I have a map from, this F is a map from metric space R to metric space Rn. What is the metric on Rn? Come on.
Sir, that doesn't matter.
Right. Well, I mean, right. So the point is, well, actually it does matter. But what you mean to say is that the metric comes from a norm. And which norm I take does not matter because all norms are equivalent, right? So remember, this is kind of an important thing, that the notions of convergence, the notions of the topology really does not depend on which norm I use because all norms are equivalent. So I can use the Euclidean norm, but I can also use the max norm, the infinity norm. And that is the one that gives me what you said earlier right away, right? That calculating the limit of a vector valued functions to be a certain vector is really the same thing as convergence in each slot, as calculating the limit in each slot, right? The ordinary real limit. Okay, good. So this is all right. If I have m equal to 1, But what do I do now if I have some function? But what do I do now if I have some function that is from a larger dimensional space? And so let's take another example. So another case. So let's draw a line over here. Another case. So the case when if n is equal to 1, then we have something like, then what we have is that we have a single real number as an output, but we have several variables, right? Some function from u, which is in R, what do I have? Rm, a real value function. So let's just write down, for example, let us say something like, let's say f of x, y, z equals some formula, x to the 4 sine y, z. In this case, do you know any notion of a derivative? Some way of taking derivative?
So the gradient.
Sorry, say that again, please.
A gradient.
Yeah, what do you mean by gradient?
Dou by dou x.
Right. So I can take partial derivatives, right? So here,
So just a quick question. We don't need you to be open here, right?
right. So we do not need u to be open, but if I want to take the derivative at a certain point, then I need to be able to approach that point from all directions, right?
Yeah.
And so I need to have an open neighborhood of that point contained in u.
Sure.
And if I want to consider the possibility of having a derivative at every single point in the domain,
Right.
then that means that the set needs to be open, right?
Sure.
And so for that reason, this is just the easiest thing to do. Here I have partial derivatives. So for example, and we kind of know how to calculate the partial derivatives, right? So del f by del x. So here, what do I have? What's the partial derivative of f with respect to x?
So 4x cubed times sine y.
And I kind of know what to do, right? Just think of y and z, pretend that they are constants, and just think of it as a function of x and calculate the derivative. So similarly, I have del f by del y equals what? Okay, so now x is a constant, so that goes along for the right and whatever, right? Cosine of yz, and then what? Is that all?
Z.
Times z. No, that z is a constant. So I have to use the chain rule. So I'll put z over here, etc. Okay. But let's go back a little bit. The way you have done the way we have done it here is del f by del x itself is a function, but really the derivative as a function. Before that, I have to tell you how to calculate the derivative at any given point, right? So let's back up a little bit and let's try to write down this definition as. So what is this? This is, if you want, really this is limit as. Okay, so you tell me. So limit as h approaches 0 of what? I'm trying to write down the definition of what it means to calculate this partial derivative. So what do? I do f of
x plus h.
Right.
Y, z.
So y and z are left fixed, minus f of x, y, z divided by h, etc. But let's back up a little bit. So really what we have is that, what we have is del f by del x at a certain point. Let's say the point p equals some real numbers RST, and I do the same thing. So limit as h approaches 0, and I'm thinking of this as actual numbers. So R plus H ST minus f of RST divided by H. And this is an honest to God real number, correct? So this, if it exists, real number. That is if the limit exists. Okay, so let's try to start putting this in vector notation. But that's really the same thing as limit as h approaches 0 of what? See, this point P is a vector, right? So in the vector, so if I think of E1, E2, E3 as standard basis, then P is really RE1 plus SE2 plus TE3, correct? Using standard basis. So in that case, what is this? How can I write this? So P is the point. So what is the point that I have written up there? R plus H comma S comma T as a vector, what is it? RST is just the vector V. I mean, the point P considered as a vector. So
P
how would I
plus
change?
H times E1.
Right, exactly. H times E1. And that's all. And I'm subtracting this f of P divided by H. Okay. So no mystery over here. We are just sort of rewriting things in a certain way. But now let's sort of put things together. Imagine that this f is not just a real valued function, but suppose f is a function from Rm to Rn, right? The gadget that I have written over here, that limit, does that make sense? Just check, no? What I have in the numerator now is f of some point. That's a vector, okay? So I'm subtracting two vectors, but then I'm dividing by h, and h is now again a real number. So this makes perfect sense. All right? Okay, very good. So essentially what we have done is that when we go to this more general situation, the goal situation, but if I fix any particular direction at a time, that no, I'm only going to vary x and leave everything else as fixed, then I come down to m equal to 1 situation, and I have some derivatives in that direction. Okay. So let's write this down just to really set up the notation. So definition. For f from open U in R N or M. That's what I had earlier, I hope. Oh, sorry, no, I have the other way around, no? So yeah, sorry, did I make a mistake over here? All right, so I seem to have switched my M and N compared to the notes. So please check that I'm not making mistakes. All right, so we'll continue with this. So open U in Rm to Rn. All right, so what do I do? Define ith partial derivative of f at some point A or in notation various possibilities. So del f by del xi at A or del f by del xi evaluated at A or d if at A. To be the limit that we just wrote down. So limit as h approaches 0 of f of. So what do I get now? The point at which I'm calculating the derivative is A. Remember, it's a vector. So what do I do? F of A plus something minus f of A divided by h. So what do I write over here? F of A plus what?
H times EI.
H times EI. Okay. And so let's just say that, remember, this is a map to Rn. So here, I is going from where to where? 1, 2, up to?
M.
M, correct? Because the number of variables is in the source is M. And also I have the following. If f is equal to f1 up to fn, real valued functions, then
Sir, but isn't H a vector here?
no,
Oh,
which is a real number.
Okay, sir. Okay,
right?
sir.
Sir, so is the partial derivative in the general vectors, like general r to the power n, a vector?
Exactly. So we should write this down. Is this yeah. So in this case, the partial derivative that I have is actually a vector. So okay. So, and in fact, that's a good point. Before I write this, let's write this down. So note that this is a okay. So
It's a vector in Rn, right?
exactly. So note that this this limit, if it exists, is in. I mean, just look at it semantically. F of whatever is in Rn. So this is in Rn, and we can see what vector this is in terms of tuples. If f is equal to f1 up to fn, so these are real valued functions. Fi functions, so that is u to r really. Then in fact, what do I have? Del f by del xi at A is really what?
The tuple consisting of the partial derivatives of each of the
Right.
with respect to xi.
So I just take the partial derivative of f1 with respect to xi evaluated at A all the way up to partial derivative of fn with respect to xi at A. So this is the vector. Okay. So putting these two cases together, the first case where I had the input was a single real number, but the output was a vector. In that case, I got a bunch of numbers. And here also, I am getting a bunch of numbers. So sort of putting them together, how many numbers am I getting? In other words, so given so for f from u to Rn, I get fj, the partial derivatives of all fj's with respect to all xi's. And let's say this is A here, where j goes from what to what and I goes from what to what. So j goes from 1 up to
N.
n, and I goes from 1 up to m. Because you see, I'm calculating derivatives with respect to variables, partial derivatives with respect to variables. And in the source, it is m dimensional. There are m different variables, x1 up to xn. So those are the possibilities for I. And the function itself is a tuple. The values of the function is a tuple of n real numbers. So I can regard each one of those real numbers as a function of so many variables and calculate its derivative, partial derivative. Okay. So I have in all, I get so I get in all m times n numbers. That's what I have. And so this is okay. This is all just fun and games. But I still have not really calculated. Still have not answered this question conceptually, which is, what is f prime of A? What kind of animal is this? I would like to be able to say that given this function, there is something called its derivative. And even before we define anything, the idea is that the derivative of a real function, real valued function of a real number, the derivative, whatever it was a number, right? But now we see that when I go to a multivariable situation, both in this domain and the range, then this information at the very least, I need to have m times n numbers in order to capture what is going on. So the derivative, this f prime of A, at the very least, it should be a gadget that consists of m times n numbers. That's not really a very conceptual answer, but we remember that these m times n numbers, they can be arranged most naturally in the form of a matrix. So let's write this down. So we can arrange these in a matrix of dimensions. Okay, so do we want to do m cross n or n cross n?
Sir, it depends on how we want to arrange, right?
Right. So actually, the question that I'm asking is kind of ridiculous, right? Because it really depends on what convention we make. We can make either convention. But let us remember now that a matrix is a way to encode a linear function between two vector spaces once I have chosen a basis for each one of the vector spaces. So what these vector spaces are, let's sort of put it on the side. But the function itself is from what dimension to what dimension?
Rm to Rm.
That was what my original thing was. But in this case, this function f is from Rm to Rn. So if this function itself were linear, then it would correspond to a matrix of what size?
N cross N.
Right, n by m, correct? This is how this is how sort of we make the convention, or most of us. So we will go with that. So let's so we will make this an n by m matrix. And so that means that, let's just write this down. So this is going to be here, of course, evaluated at A. And then what do I get over here? What changes? Is it F1 with respect to a different, do the X's change in the first row, or do the F's change in the first row?
I think the X, because
Right.
there should be M numbers there.
Correct, exactly. So you see it's an n by m matrix. That means there should be m columns, which means the number of entries in any row has to be m. That is exactly the number of x's. So this is that. And here I have x1 stays fixed, but f goes from, and here I have del fn by del. Okay.
So could you explain again why you chose n by n and not m by n?
Sorry, what?
Can you explain again why you chose n by m
Correct.
dimensions?
So now the thing is, we have to, so the reason for this choice is that a linear map, I mean, this is really, let me put reason in, reason in quotation marks, because this is just heuristics at the moment. Is a linear map from R m to Rn is encoded by an n by m matrix. So what is the linear map? You see, I mean, right at this point, it is just some kind of heuristics. F is not a linear map. F need not be a linear map. But somehow I'm saying that, look, my given map was from Rm to Rn. So let me use the same convention that I use for linear maps from Rm to Rn. That's all that this is. It's kind of a weak argument. But the way I'm trying to motivate this is by saying that, look, the information that we already have about this function f can be encoded by a matrix. A matrix stands for a linear function. So perhaps the derivative should be thought of as a linear function. So, as a linear map from Rn to Rn. So I have to put this in quotation marks, because so far we have no idea what f prime of A is, except in the simplest situations that we saw earlier, when the domain of the function is R, right? But now I want to make this sort of an intrinsic definition. What is f prime of A? Right? And So this is a new way of thinking, and you really have to get used to this. So what is the idea? So in one variable situation, so in the old situation, so of f, let's say from R to R, f prime of A is a real number. Okay, but this real number, I can think of this is a 1-by-1 matrix. So when I think of a 1-by-1 matrix, and if you want to think of it as a linear map, what linear map is this? Let's say I take the real number 3. What linear map does this matrix encode?
So x goes to 3x.
Right. Okay. So okay, is a 1-by-1 matrix, and as such, so it encodes a linear map from R1 to R1. And what is the map? X going to f prime of A times x. Okay. So this may appear very strange, but it's actually very natural. Think of what happens, think geometrically. After all, what is derivative? It is local linearity, right? So what is this local linearity? So let's just write down. So this is not terribly. Let me see, at least if I can do somewhat better. Okay. So this is the graph of x square, and so y equals x square, and let's say I take the point 525. So the derivative is 10, but really this is the tangent line, right? So slope is 10. So what we can now think of is that really this tangent line is the graph of a linear function. Okay. Do not think of the tangent line as a graph embedded in the same plane. Okay. So this can be thought of as this tangent line as the graph of a linear map from R to R, taking x to 10x. And maybe we should not even say x. Let's use maybe some other letter. Oops, okay. I don't know what. So, okay, so let's use maybe t. So what you think of is that this point itself is an origin in some other plane, okay? So I'm making this point to be the origin and setting an x and y axis over there, which are parallel to the original x and y axis. And then you see the equation of that line really just becomes y equals 10x or y equals 10t, right? So in this sense, the 10 is really encoding this variation along the tangent line. And you sort of see that this is, imagine some particle is traveling along this, right? And let us say at this point, it just sort of falls off. It's no longer constrained along the curve, but it just falls off. Then it will go along that line. And what will be the speed? The speed will be 10. So its position at any given time will be given by 10 times t compared to the origin. So, so this is how I think of this derivative not as a number, but as a linear map. All right. Okay, very good. Then here's how I can reformulate what the derivative means. F prime of A okay, you know what? Maybe I want to do something else. Let's not even call this T. Let's call this even more suggestively. Let's call it H. Okay, so then F prime of A is a number such that, or not then, I can think of it like this, is a number such that limit as H approaches 0 of F of A plus H. So, right, so we are still in this old situation. So F of H minus F of A divided by H. This is equal to F prime of A, right? But that really is saying the same thing as minus F prime of A. What is this limit?
0.
0. Okay. So let's now put this over a common denominator. And let us say that this is the same thing as this is the definition that we are now going to try to generalize. So inspired by this, for A in U, F to Rm. So this is U open in R. Sorry, I keep switching. This is in Rm and this is in Rn. Define F prime of A is something or the other such that. And now let's just try to write this down. Limit as H approaches 0 of F of A plus H minus F of A minus and I want to divide this by T. And I want the limit to be 0. So first of all, I want to divide by H. There is no dividing by a vector. So where does H lie? Let's remember. So remember that H is something in R what? Rm. So there is no dividing by that. So what I get to do is I get to do this. Now up there, I need to have a vector, correct? But I need to have F prime of A in there. So what do? I just write the same thing, F prime of A, H. But now what does this mean? You see, H is a vector. And I'm taking F prime of A to be some gadget that I'm multiplying with this vector in some fashion, right? Let us recall what our goal was, at least heuristically, that F prime of A can be defined as a linear map. So if F prime of A is a linear map from from Rn to Rm, sorry, just 1 second. I think I've sort of No, sorry. So that was a mistake. Remember, my original F is from Rm to Rm. So that was a mistake here. Right. So F prime of A is supposed to be a linear map from Rm to Rm. And H is a vector in.
RM.
So what does F prime of A times H mean here?
Then RM.
Yeah, but that times is really should be thought of as application. You see, in the, in this earlier one variable example, what we said is that this F prime of A times H. So remember, F prime of A was some number like 10, for example. So 10 times H was really also the same thing as the linear function encoded by the matrix, singleton matrix 10, applied to the argument H. Yeah. So that multiplication is really application of the linear map. So over here, what I want to do is I want to interpret this. So F prime of, we define F prime of A. To be a linear map from Rm to Rn such that this limit equals 0. Now this limit equals 0. I can define. So this is a perfectly good definition. All right. So here H.
Sir, it's in the right hand side, it's a zero vector or
Right. Correct. So exactly. The way I have defined it, should it be a zero scalar or zero vector?
zero vector.
Right, because the top is really a vector. Now, however, notice one thing. We are working in a non-linear space. So what I have written over here is an equation that is valid in. So let's say this is true in what? In Rn. Okay. But now notice one thing. If a vector valued function having its limit as H approaches whatever 0, that's okay. The vector valued function having its limit as the 0 vector is really the same thing as the norm of the vector valued function, that you just apply the norm to that vector valued function to get a real valued function. And what should happen to that norm? Since the vector is going to go to 0, the norm will also go to 0, right? Because the norm of the 0 vector is 0 and the norm function is continuous. Remember, norm function is continuous. But also converse is true, right? If the norm of some vector valued function goes to 0, then the vector also has to go to 0. Why?
The only vector that's 0 is that
Right.
has non-zero.
So I can define it in this fashion. And then, so this is how in R. So here, so this is an important thing to note here, that note that F prime A H is equal to value of linear map F prime of A applied to the vector H. So this is really application. So if you really want, You can, so in more form, this is how, maybe if you want to write it this way. But the left hand notation is also okay, because you see, if I encode the linear map as a matrix, then evaluating the map on a vector is really the same thing as matrix multiplication. So it's a perfectly reasonable notation. The left hand side is also a perfectly reasonable notation. All right. So this is a new viewpoint, all right? So, and you have to sort of get used to this. We are out of time, so let me just sort of lay out the next few considerations, and you should try to do some of this by yourself. Okay.
Sir,
Yes.
so why did you put the norm on the numerator then?
Well, this is sort of the standard definition, but what I try to justify is that if I put the norm versus if I don't put the norm, it doesn't really make any difference.
Oh, okay. Because the vectors also converge to 0.
Yeah. So a vector converging to 0, a vector valued function converging to 0 is really the same thing as the norm. I mean, one way it is easy, because if a vector goes to 0, its norm is going to go to 0. But if a bunch of vectors, but if a vector valued function, if the norms of those vectors go to 0, then the original vectors also have to go to the 0 vector, you see, because only the 0 vector has 0 norm.
Yeah. Okay.
All right. So, so one is, why are we doing this? So first of all, here is the so exercises. So this exercises, which is if f prime of a exists, then it is unique. You see, the way the definition is there is that f prime of a is a linear map such that this limit is 0. So perhaps more than one linear map will do the job. But that's not the case. And you can just sort of do this for one variable situation to see how this is going to play out. This is not a difficult proof. We will do this the first thing next time. But now, so to connect it with the way I try to motivate this is that suppose this f prime of a exists, then matrix of f prime of a with respect to standard bases of Rm and Rn is precisely the matrix of those partial derivatives. So what did I have? Fj, what do we call them? Fj by del xi. And then various things. So, for example, if f prime of a exists, which we are going to say this means that f is differentiable at this point a. Then what? Then f is a differentiable function in particular is always continuous. And so various things. So remember what we said at the beginning of the semester. What you did in the first semester for functions of one variable, now we want to do for functions of multiple variables. So chain rule, mean value theorem. So there is a whole lot of work to do. But the very first thing that I want you to wrap your mind around is that now the derivative is not a number. It is a bunch of numbers arranged in a rectangular fashion. That is the first level understanding. But really, the derivative is a linear map. Okay. Why we want to think of this as a linear map? You will appreciate more with time. And we will discuss it a little bit after class. But right now, I do not want to continue the class anymore. So let's stop and we will continue next time. But do try to do these exercises for yourself.
Recording stopped.
Okay. Yeah, so I'm in the process of compiling the various exercises that I have given in class. And so you should be getting a homework very soon. All of these exercises are available in class notes, and I hope that you have been writing the solutions. Okay, if you have not, then this weekend is the time when you really do need to sort of get on that. The next thing is yeah, so I really would like to get a temperature from the class. So maybe next week what I'll do is I will require people to come and meet me during office hours. So I'll inform you on Monday how I would like that to happen. If you have any difficulties, then that is a good time to let me know, so that we can figure out how how to make a work plan, or how I can help you or clarify your doubts, whatever. Okay, so are there any questions? If there are any questions, then I can discuss. Otherwise, I also want to maybe just draw a little picture to try to motivate why it is that I'm not satisfied with thinking of all of these various partial derivatives arranged in the form of a matrix. Why I would like to have this more abstract viewpoint of thinking of the derivative as a single entity and as a linear map between two vector spaces.
Sir, I had a question there. So
Yes.
all our results for Rn will also work for normed vector spaces, right? Using that isomorphism.
Sorry, so can you be more specific? What do you mean?
Sir, when we covered the topology and all that, we proved many theorems only for Rn. So all
Right.
that will work for normed linear vector space, right?
Finite dimensional non-linear space.
Yeah, finite dimension.
Yes.
Okay.
But you see, you have to be a bit careful, because by all you mean things that can be transferred from one to other by means of a vector space isomorphism. Okay, just to give you an example, see for example, if you think of R2, and let's say the plane as in the Euclid's plane, okay, and you fix some origin, then to say that an element of R2 is that every vector in R2 is an ordered pair, okay, right? Does that mean that a point in plane is also an ordered pair, that is equal to an ordered pair?
No.
No, right? I mean, a point is a point. You see? So the statement that I want that, so for example, if I say take the first element of this ordered pair. Now, if I try to apply this statement to a point in the plane, then a priori it makes no sense. I have to use a dictionary over here, right? Okay, let me put it this way. The only reason why I don't want to say a wholehearted yes is that you said any statement that I have for Rn is valid for a vector space. Then you have to really specify for me what you mean by any statement. Are you going to say are you going to say something like, okay, what is the color of this point, or what is the color of this vector, or something like that? I mean, just to give a ridiculous example, right? So any statement that can be encoded purely in terms of the vector space operations is as true for that vector space as it is for Rn, where n is the dimension of the vector space.
Okay, sir.
So then I guess you would need the vector space to be real also, right?
Yeah, right.
Yeah.
So yes, absolutely. And so in this course so far, all our vector spaces are real. And at some point we will talk about complex vector spaces. But for us, vector space means real vector space. But the point is valid. If I have vector space over the 2-element field, then absolutely nothing that we have said makes any sense whatsoever. Yeah. So regarding this, regarding these partial derivatives, so why am I not happy with just saying, okay, just del f I by del x j or something, right? Okay, so here's one thing. So imagine that you have some paraboloid. Okay, so let me see if I can draw something like this. So let us say I have something like this. Okay. So this is really a function from R2 to R. Yeah. Where the domain is this. That is the domain. And the height is so I have drawn the graph of this function. All right. Now, if I look at any point, then, so sorry, let me just see what I want to say. No, this is not real. This is not really good. So, or let's not take this, because okay. So what?
You will take care of this.
So you think of some surface. The point that I'm trying to make is that maybe not even this. Sorry. So I did not plan this, so I have to sort of fumble my way through this a little bit. So imagine that you have a function of two variables and the value is given by the height. So you see the graph of this function is going to be some kind of terrain, right? Imagine that it's like some kind of, it's going to be some kind of surface. So the height will increase, decrease in some way. There may be some hills, valleys, etc. Yeah. Okay. So now you see, if I want to study the geometry of this or what is going on, the variation of this height, if I put in, okay, if I come with my coordinate axes there and put some X and Y axis, right? Then I get to calculate, okay, what happens if I walk in the X direction and what happens if I walk in the Y direction? Am I going up or am I going down? What is the slope? That's what those that's what those partial derivatives are going to calculate, right? But really, this X direction that I put and the Y direction that I put, that's an artifact, right? It is something that I put there. Somebody else may come and put some other X and Y direction. So you see, to have a straight jacket that this is X and this is Y, it may not be intrinsic to the situation. Somebody else may choose a different coordinates. Or even if I choose some coordinates, what may happen is that why should I be constrained in walking only in the X direction or Y direction? Maybe I want to go in some completely different direction, which is a linear combination of X and Y. And then you see, I'm going to have some kind of trajectory even over there, right? The height is going to increase and decrease. So I have derivatives not just in X and Y directions, but I have derivatives in all kinds of directions. So let us go back up and see how this definition of partial derivative can be adjusted to take derivative in any direction. So it's straightforward, right? If I want to, so let's just say I have look at this definition, for example. If I want to calculate the derivative, the derivative at a point P in some direction V, what do I do?
I think we could
Take the
replace E1 with
unit vector along that direction.
Yeah. So the only thing that I change in this definition over here, what do I do? I make only one change. Now I don't want to go in the X direction. I want to go in some other direction. So that direction will have a direction vector V, right? What do I do? In this definition, I simply replace what do I do? So this was partial derivative in the X direction, and that is and I have that the X direction is encoded in this limit in what way?
Through E1.
Through E1. So I simply replace that E1 by a vector in whatever direction I like, and I get the directional derivative in that direction. Okay. So you see, geometrically speaking, there is no reason to prefer any one direction over others. All of those are equally valid directions. And that means I should really be considering all directional derivatives. So when I start thinking of this derivative as a linear operator, conceptually, it really does take me in that direction. That this derivative as a linear operator, I can evaluate on any direction vector and get the value of the derivative in that direction. So this is just for a function of one variable. But for functions of multiple variables, the same thing is true. You see, in this terrain example, my output was only one dimensional. But if my output is also in multiple dimensional, then maybe I want to think of that also as a vector intrinsically, rather than in terms of its components. So thinking of this matrix really more as a linear operator is the more intrinsic way of thinking about the derivative. And one of the things that sort of tells you that this is the sort of a very good way of conceptualizing it is that you may have seen chain rule for various I mean, if you have done any multivariable calculus before, then you see there are various chain rules. So if you have a function from Rm to R1, versus if you have a function from R1 to Rn, and if you start composing these functions, and then if I start calculating the derivative of the composite, the chain rules take various forms. But if I think of the derivative as a linear map, then the chain rule becomes extremely simple. If you have a map from Rm to Rn to Rk, if I have functions from Rm to Rn to Rk, then the derivative of the composite function at any given point is simply going to be the composite of the derivatives. Remember, the derivative is a map. So to calculate the composite of these two maps makes perfect sense. And if you think of real numbers, again, if you think of the chain rule as, so let's write this down in this terrible way. So chain rule, what does it say? For f composed with g, its derivative at a is f prime of g of a times g prime of a, correct? So, but if you think of these as linear maps, then you see a linear map from R1 to R1 is multiplication by a number. And another linear map from the target R1 to yet another R1 is also multiplication by a number. The composite of these two maps is going to be multiplication by the product of these numbers, right? The composite of x going to 5x and x going to 7x is x going to 35x. Because the first map is multiplication by 5, the second map is multiplication by 7. So when I compose these, I get multiplication by 35. That's what that chain rule is. So this is a very good way of thinking about derivatives, and with time and experience, you will just come to see it as natural. So for now, to get used to this, if you doing this exercise number 2 would be a good practice. And for that, so I should really stop now. But for that, you have to remember how to write the matrix of a linear transformation. That means you have to go back and revise your linear algebra if necessary. Now, if you would like to have some review of linear algebra, basic linear algebra, I'm perfectly happy to conduct it. Maybe are the class reps here? Sorry, so who are the class?
I don't think they're here at this moment, but we can talk to them.
Yeah, okay. So, but maybe somebody in the class, what you can do is you can conduct a survey among yourself as to what extent you would like to have a review of linear algebra. I'm perfectly happy to sort of have spend one class on it, or maybe half a class. But if you want something more than that, then we should do it outside of class. So we can arrange some sessions where just the very basics of linear algebra, which is what is a vector space, how do you, what is a basis, what is a linear transformation, and after fixing a basis, how does a linear transformation become a matrix? That basic part I can revise in maybe a couple of lectures. So that's sort of up to you.
Okay, so we'll talk to the representatives.
Or whoever, it doesn't matter. So just set up some kind of poll and see what see what people would like. Basically, this second exercise you should be able to do without much difficulty once you understand what the definition of this f prime of a is. Okay, so this is all that I have for today. And unless there are any questions, we can stop.
Sir, I had a question.
Yes.
Sir, f prime of a is like we can take it as a matrix or a linear map, right? So
Yes.
so what does a linear map do to any vector in Rm?
Sorry, say that again.
So we are taking f prime of a into f prime of a times h to be
Right.
the linear map applied to h, right?
Yes, exactly.
So if we take it analogous to the real to real case, it would be
Yes.
could be just multiplication.
It will be just multiplication. Yes.
So this map is something analogous to multiplying with a vector. Multiplying.
Yes, right. But that's exactly how the encoding in terms of a matrix looks, right?
Yeah.
So the matrix of a linear, so let's call a linear map. I don't know what you call it. T, maybe T for transformation. So T of V, after I fix a basis, T of V is really the same thing as the matrix of T times the coordinate vector of V. It really is matrix multiplication. That's how the dictionary works, right?
Yeah.
Okay, so is there anything else? Yeah, so once again, if you have any questions, if things are, then feel free to call me. If you do not reach me, the best way is just to send an SMS saying that you're trying to reach me for the course, and I'll call you back. We are at an interesting stage in the course in that whatever we did in the first, whatever 1/3 or, first, whatever 25-30%, really only a limited part of that is required. You just have to understand what open sets are. And open sets are locally open. You have wiggle room everywhere. That's enough to go on with. So if you have some difficulty in the first part of the course, then this is a chance for a reset. All right. So if there is nothing, then we will stop for today and we will continue on Monday. So bye, everyone.
Thank you, sir.
Thank you so much.